So if you ask a mathematician about groups, odds are they might tell you something about symmetries. Symmetry, of course, being a way to sort of move something so that it then looks the same as it did. Um, so I'd like to try and show how groups and symmetries are kind of connected in this video. So one way to change this sort of triangle, maybe I'll number my vertices of this triangle. This will be vertex 1, vertex 2, and 3. So if I have a triangle, I can rotate it. For example, rotating it like this. And then I'll get another triangle. That'll look maybe something like this. Maybe I'll just write a little triangle up here, and it'll be 1. 1 will rotate this way, 2, and then 3. And so this sort of rotation, if I rotate it, if I didn't have these numbers here, this triangle would look exactly the same. And that's what makes it a symmetry. So other than rotating, what can I do? Well, I rotated one way, I can rotate the other way. So if I rotate the other way, my vertices are going to look like this. I'll have 1 on top now, 2 will be over here, and 3 will be over here. Maybe I'll write another little arrow here to show that that's where that sort of came from. Another thing I can do is I can try to reflect this triangle. And the way I'll reflect is across this vertical axis here. All right. And so if I do that, well, the third vertex is going to stay where it is, but 1 and 2 are going to flip. So if I'll write that up here as with right here, I'll have vertex 3, 2, and 1. And then because a triangle, again, is a symmetric object itself, I can rotate across this axis over here. I'll put this over here, and I'll put this rotation. So 1, 2, and 3 are now flipped, and then my last one, I might not even write it here on the big triangle. It's just reflecting across this other one, and my vertices will be, well, let's see, 1 and 3 will be flipped, 2, 3. And last but not least, I have the identity symmetry. Do nothing at all. Well, okay, it looks like it did when I start with, but that's pretty trivial. But we're going to need an identity if we want to have some sort of a group, as we know from the axioms. So what does a mathematician mean when they say that the symmetries form a group? Well, we're going to regard not the triangle itself or the vertices of the triangle, but the actual symmetries, right? These things right here, I've drawn little diagrams of as the elements of the group. And if you don't believe me that these are all the symmetries of the triangle, I guess it's sort of obvious from looking at it. But there's a theorem in mathematics that's called the classification of isometries. You can look that up, and one particular consequence of that theorem is that these are the only symmetries of a triangle. Okay, now our group, so the elements in our group are going to be these symmetries. So let's call this identity symmetry E, the identity element. And then let's give names to all of the other symmetries. And so the names are going to be, maybe I'll call this one X. This one's sort of like it, so this will be X prime. These are sort of different, so maybe I'll call them Y, Z, and W. So now what I'll do is I'll define multiplication of symmetries in the following way. So multiplication, so there's 3 vertices. This set is going to be called S3. It's going to have E, X, X prime, Y, Z, and W inside of it. And S3 is going to have a multiplication, so that's going to be a function from S3 cross S3 to S3. And what I'm going to do is I want to compose the symmetries, meaning do one after the other. And I want to do it in the following way. If I have something like X, Y, I want to do the one that comes on the right first. So this would be, first I'm going to rotate, or no, Y is a reflection. First I'm going to reflect. So this is now 2, that's now 1, just like this. And then, finally, once I've done that, I will rotate based on X. And then, so then this will go away. So this will be, this will turn to 3, this will turn into 1, and 2 will come here. And if you were watching closely, you will notice, or wait, I did this wrong, didn't I? Yes, I did. So 2 should have been on this side, and then 3 should have been down here. So we should have had 1, 2, and 3. There we go. If you want to see my mistake, you can go back in the video and look. Now, what you notice is that this permutation, once I've gotten the vertices here, that is what the new permutation is going to be. And in fact, if you look at it, it turns out to be Z, right? I have vertex 1 on the top, just like Z, vertex 2 over here, and vertex 3 over here on the bottom. And what that shows is that, well, if I do this for all of the symmetries, I'll see that if I keep composing symmetries, I'll get another symmetry. That'll be what I need to have this function be a real multiplication, be a multiplication law. If you want to tell that this is associative, you have to kind of manually check it. I'm not going to do that because it's kind of hard. If you want to tell that there's an identity element, that's pretty easy. You just take the identity transformation that doesn't change any of the vertices. And last but not least, if you want to see that there are inverses, well, you can look at each of the elements sort of by themselves. Each of these reflections is its own inverse. And then this, actually, these 2 rotations, they're not like the reflections. They're not their own inverse. But if you do one after another, then you'll see that, well, X inverse is actually equal to X prime, right? If I rotate one way and rotate back, I'll get the same thing. Another thing that you can see is that X times X, so if I first rotate by X, then I rotate by X again. Maybe I can even do that in my big triangle here. I'll start back from the identity, 2, 3. I will rotate once, so I'll rotate here, and at this point I have rotated once, Now I will rotate again. Rotate, rotate, and I have back exactly this x prime right here. The vertices are in the exact same spots. So that means that x times x equals x prime. And when mathematicians talk about this, we don't even call this x prime. We just call it x squared, right? This is x squared. And in fact, when we have z, we call z xy. We want to have as few letters as we can. So we'll just call this element x times y. And as a sort of last thing, maybe let's check to see this final sort of relation that x squared y equals w. Or you know what? Maybe I won't do that. But it's exactly the same sort of thing as we did earlier. So we can replace w with x squared y.